the kernel and range of a linear transformation. Uh, Here, the concepts of the kernel and the range are two of the most important concepts in linear algebra. Basically, where we started from in chapter one, we end up here in this late chapter, talking about really the same concepts in terms of being able to use row reduced echelon form, looking at the ones along the main diagonal to determine the so-called rank, and then looking at the zeros on the main diagonal to determine the nullity. With that said, the vectors that constitute the rank is said to be the range, and then the vectors that constitute the nullity is said to be the kernel. So we'll look at all of that, determine whether a transformation is one-to-one or also onto, and then we put both of the concepts together, one-to-one and onto, to form a bijection or a bijective function or an isomorphism. So the definition of a kernel of a linear transformation: let T map vectors from V to W be a linear transformation, then the set of all vectors in V, the set of all vectors in V, the set of all vectors little v in capital V, that vector space V, that satisfy T of V equal to 0. The kernel wants to find out what vectors are mapped into 0. So this is called the kernel of T, and denoted by KER of T. Graphically, we look at this transformation. The standard function terminology is used for here for these functions. Here, V is the domain of T, you recall from the previous section, and W is the codomain of T. If V is in, little v is in V, and little w is in big W, such that T of V is equal to W, then W is the image of V, and that's taken directly from the idea of functions from algebra. The set of all images of vectors in V is said to be the range of T. You remember from algebra we said that the range is where the function is going, and the domain is where you're coming from. And so then the set of all little v and capital V, such that T of V is equal to W, is said to be the pre-image of W. And so you notice here how the idea of the range could be smaller than the codomain, and that's possible. We talk about later about function or transformation that's onto, and that basically means that the range is actually equal to W. So so the function fills up all of where it's going. It fills up the vector space of where it's going to. Here, the kernel, that's the theory, the theorem for the kernel. The kernel is the subspace of the domain V. The kernel of linear transformation T is a subspace of the domain V, and I thought that was pretty good consequence there. The corollary, this idea that stems from the major theorem, let T be a transformation that maps vectors from Rn to Rm, be a linear transformation. This linear transformation is no more than the multiplication of the matrix A, and indeed you see that. So that transformation is no more than just sophisticated terminology for multiplying a vector x times A. Then the kernel of T is equal to the solution space of AX equal to 0. Now that's important because we've been doing that already. You set AX equal to 0, you solve basically the homogeneous system, and the values of x that you get are said to be the values in the kernel. All of those values collected is said to be the kernel. The range of a linear transformation, the definition, the range of T, it maps V and vectors in V into vectors in W is the set. This is the range, the set of all vectors W in capital W that are images of vectors in V. And I thought mathematically to write it in terms of what we know from set theory, the range of T is equal to here um, all of these images T of V, such that little v is in V. So the range says that we put the claim on where we're going, and then if that exists, then obviously what produced that has to also exist from the domain. The theorem that follows, the range of T is in the subspace of W. Here, the range of a linear transformation, T, is also a subspace of W. So you get the range, the subspace of W, and the kernel is the subspace of V. What does that mean? The kernel is the subspace of the domain, and then here the range is the subspace of the codomain. Pretty interesting. So the kernel has a lot to do with where I'm coming from, and the range has all to do with where you're going. So here's just a graphic image of that. The kernel is a subset of the domain, and then the range is a subset of the codomain. Sometimes we make an error in our terminology by saying that the range is the codomain. When that happens, then you're really talking about an onto function. We'll see in just a moment. Here's the corollary that stems from all that. Let T be a transformation that maps vectors from Rn into the Euclidean vector space Rm. Both are Euclidean vector spaces Rn and Rm. Here be a transformation of T that's defined by matrix multiplication. Then the column space of A is equal to the range of T. So that's really just a fabulous conclusion, that the column space of A is equal to the range of T. I don't think we'll use it, but no, I'm just, yeah. But anyway, that is a good consequence to come to. A definition of the rank and the nullity of a linear transformation. Again, these are repeats. We've talked about rank and nullity in previous chapters, and particularly there in the chapter for vector spaces. Here, let T be a transformation mapping vectors in V into vectors in W. The dimension of the kernel of T is called the nullity. So the dimension is just the number of vectors in the kernel is called the nullity. We found this already before, and that's denoted as the nullity of T. So whether they say, the linear transformation of T or the matrix A, we're pretty much talking about the same thing. The dimension of the range of T is called the rank of T, and it's denoted by the rank of T. So basically, here in this chapter, they've just changed the wording from saying and claiming matrix A to a transformation T, which, talking about the transformation T, generalizes this discussion. The sum of rank and nullity, again, we've looked at that with respect to matrices. They just apply that same idea, and it's just a copycat now to the transformation. So T, which represents basically matrix multiplication of A, the sum of the dimensions of the range and kernel is equal to the dimensions of the domain. That is, the rank of T is equal to the nullity of T. The rank of T plus the nullity of T, is equal to N. That rank is the dimension of the range, and that nullity is the dimension of the kernel. And that's equal to the dimension of the domain, which we just say is N. Now, one-to-one and onto, I'm just running through the topics, and then at the end we'll put it all together in a few problems. One-to-one and onto linear transformations. Now, this is just a copy from algebra. Definition of one-to-oneness, a function T that maps vectors from V into vectors in W, is one-to-one when the pre-image of every w, that preimage, you're talking about vectors in the domain, of every w in the range consists of a single uh, vector. And we're trying to do our best to try to illustrate this as well, just to refresh your memory. Um, so, so recall the definition of one-to-one from algebra. A function f is one-to-one if for all x sub 1 and x sub 2 in the domain of f, x sub 1 and x sub 2 are different. So for all distinct values in the domain of f, that implies that the image values, the function values, are also distinct. If this happens, then we say that f is said to be one-to-one. You recall that the test used to determine one-to-oneness was the horizontal line test. The vertical line test was to determine if the equation was indeed a function. Further, recall that if a function in algebra was one-to-one, or it satisfied the horizontal line test, then you were able to conclude that the function had an inverse. What's the point? The notion of one-to-one in pre-calculus algebra is the same here. We're talking about the same thing. Actually, the concept comes from here, this study of this course, linear algebra, and thus all of its subcomponents, like algebra and calculus, received the good news also and borrowed the concept. So let me look at this, and then we'll come back to the example from algebra. So you talk about one-to-one, and according to my illustration, say for example this is x sub 1 and this is x sub 2. So indeed the function value f of x sub 1 is different from f of x sub 2. Now this down here is saying that if this was x sub 1 and this is x sub 2 and they're both mapped to the same value, just call it f of x, then this is not one-to-one. So you get the idea of one-to-one. For one x value, there's one y value or one f value, right? So here, x sub 1 is different than x sub 2, but that implies that for this particular problem, that f of x sub 1 is the same as f of x sub 2. So we get equality there. So that's not supposed to happen, right? Now let's look at just borrowing something from algebra. From algebra, show that this function f, this parabola, is one-to-one. If it's not, then redefine the domain to get one-to-oneness. So if you look at some values from the domain and the range, so if we have 1, you square that, you get 1. If you have negative 1, you square that, you get 1. Uh-oh, you see how that's the problem? Let's just do 2 more. 2 and 4, negative 2 and 4. Again, we have something that's not good. If we look at the graph of this, so whether you do the points or you do the horizontal line test, the horizontal line crosses the graph at 2 points, supposed to only cross at 1 to satisfy the horizontal line test. So we conclude that, let's see here, notice x sub 1 is equal to 1, x sub 2 is equal to negative 1. X sub 1 is different than x sub 2. But f of x sub 1, which is equal to 1, that's the same as f of x sub 2. Thus f is not one-to-one. So as it stands, this function uh, does not have an inverse. But we can redefine the domain. Uh, as of right now, the domain would be all real values. So here for this one, the domain is equal to, for all x, such that um, x is a real number. And there's several ways you can write that. You could say negative infinity is less than equal to x, less than or equal to positive infinity. It says the same thing. So here we can redefine the domain. To force one-to-oneness. So define the domain to be from 0 to positive infinity. And you could have also chosen from negative infinity to 0. So that means in terms of the graph, we're only looking at this side. So now when you apply the horizontal line test, it only crosses that graph just one time. Basically, this domain kicks out those negative values. It's not supposed to happen. Kicks out those guys, right? And so then from there, you do get one-to-oneness. And so with the redefined domain, f is now one-to-one. And you recall from there you could find the inverse. You can only get the inverse if it's one-to-one. So let y equal to x squared, solve for x. So this implies that we have plus or minus the square root of y is equal to x. We change y to x. We change x to f inverse. F inverse of x is equal to just the square root of x. We don't need the negative because you recall that the domain of f is the same as the range of f inverse. So the range values obviously would take up plus and minus, but for the range of f inverse to match the domain of f is only taking up positive values because we've restricted that. So thus we exclude the negative values here for the range of f inverse because the domain of f has to match the range of f inverse. So that's why we don't have plus or minus over here, right? Well, that's just something from algebra, but what we did back there is exactly what's being called for here. So nothing new under the sun. So this theory one to one. This is a good theory. This is the one that I use. One, how can we figure out if the transformation or the system is one to one? This theorem says that T is one to one if and only if the kernel only maps the into zero. Okay, so that's what we'll use. So keep that in mind. That to determine one to one, we want to find the kernel. Well, the kernel is no more than just the solution space for AX equal to zero, and we want to make sure that we get all zeros for the solution, basically the trivial solution, right? If not, then it's not one to one. Now the definition for onto a function T maps from V into W is onto when every element in the so-called range in W where you're going has a pre-image over in the domain in V. So in other words, T is onto when W is equal to the range of T. Powerful statement, right? Now we can write it out formally here that T is onto if for all little w vectors little w that are elements in W, here this codomain, there will exist a vector V in this big vector space capital V, the domain, such that T of V is equal to W. Now, and just to make sure you get a hold on it, T is onto when all of W is used up. Beautiful stuff. Because a lot of times with functions, you're not using up all of the values in the so-called codomain or range, and we've probably been miscalling the range out of term, but maybe we can get it right. So this theorem is helpful. So in terms of being able to kind of pinpoint exactly what they're talking about in terms of onto when it comes to systems of equations, let T map vectors from V into W be a linear transformation where W is finite dimensional. That is that W contains vectors that are countable. You can count them all. And to be exact, the dimension of W is countable. The number of vectors in the basis, there's n of them I can actually count. Sometimes we can deal with infinite dimensional vector spaces. So then T is onto if and only if. So T is onto if and only if the rank of T is equal to the dimension of W. Now this dimension of W will be the number of rows that you have. The number of rows is the same thing as the number of vectors in a column, right? So we get one to one if the kernel is equal to zero. That is that the solution space for AX equal to zero, we only get values of zero, and we get onto when the rank that we can find is exactly equal to the number of rows. So this next theorem, one to one and onto, let T be a transformation mapping V into W, and it's doing that by some matrix A, and that's matrix multiplication. Here with these vector spaces, obviously V and W, both of the same dimension, and you got to have that, because that's the kicker here. If V and W have the same dimension, and then T is one to one if and only if T is onto. So if these vector spaces, the domain and the codomain, of the same size, then if you get one to one, then you automatically for free get onto. Now here is just a diagram just to conclude everything. And what they're doing is looking at these four matrices over here, trying to determine the nullity, the rank, and determine whether or not T is one-to-one, onto, or neither. So let's first look at this and see if we can get the, if you recall the rank. The rank would be looking at once the matrix has been reduced, and these have been reduced. So you look at the leading ones on the main diagonal. Um, and let me write for each one here that this is n is equal to 3, n is equal here to 3, n is equal to 2, and then n is equal to 3. And I think I got that right, especially for B and C. If not, I'll try to come back. Um, so so n is equal to 3, and I'm looking at, in terms of n, just the number of rows that we have. Um, so when you come over here, you get this so-called dimension of the domain. Basically, you're just looking at this size here. So the dimension of the domain would be here, n is equal to 3, n is equal to 2, and I suppose I'm just working backwards, right? That's where this 2 comes from. That's where that 3 comes from. That's where that 3 comes from. That's where that 3 comes from. Because it's interesting, in linear algebra we have, there's one theorem that deals with n is the number of columns, right? And then you have some that talk about the number of vectors that you have in the row. So no problem. Now let's look at, I'm going to highlight here my leading ones on the main diagonal. So look at the leading ones here. I have 3 of them, so that's why that's the rank. You remember, by reduced row echelon, look at the number of ones you have on the main diagonal to determine the rank. Here we have 2 for part B, so that's 2. We have 2 leading ones for part C, so that's 2, and we have 2 here for 2 leading ones for part D, and so we get 2 here as well. Now to get the nullity, you just subtract 3, the dimension of the domain from the rank. So here we're just doing a subtraction. To get the nullity, the number of vectors in the kernel. So 3 minus 3 is 0, right? Two minus 2 is 0. 3 minus 2 is 1, and then 3 minus 2 is equal to 1. So now the question of onto. Well, let's do this. There's a theorem that says that if the vector space V is the same as the vector space for W, that is, they have the same dimension, then the theorem says, and I could probably back up to it, that that if it's one-to-one, then it's also going to be onto, and then vice versa. If it's not one-to-one, then it's not going to be onto, that kind of thing. So what the theorem says is that if the dimension of the domain is the same as the the dimension of the range, that is the dimension of the domain, is the same thing as the rank, then automatically it's going to be one to one and onto. So that'll be yes and yes. Now again, if they're of the same size, so notice we get 3 and 3, and here's 3 and 3. They're the same size, but over here these numbers are different. The numbers supposed to be the same for them to be both one to one and onto. But since they're different, then the answer there is no and no. Okay. So that's how you get that. Now, in terms of one to one, just going directly at that, we said that the function or the transformation is one to one if the kernel is only the zero vector. We get the kernel that only maps into zero. So if you look at part B, come back and look at this matrix. What that says is that when you solve AX equal to 0, would you get x of 1 equal to 0 and x of 2 equal to 0 for this one? Yes, you will. Yes, you will. So here we get the 0 vector here for the null space, x equal to 0. So that's why this particular matrix there is indeed one to one. Now come look at part C. Part C, you're going to have infinitely many solutions because of this column right here. That is that x of 1 is going to depend on some value of x of 3, and then x of 2 is going to depend on some selection of x of 3. So that being said, I don't get the trivial solution. I get infinitely many solutions. Since I have infinitely many solutions and not the trivial solution, then you conclude that it's not one to one. Now, in terms of onto, we said that if you go back, we can kind of scroll back to it. This is the theory that we use, that T is onto if and only if the rank, so we got that rank, is equal to here the dimension of W. See, W is the domain, right? So here that's equal to the number of rows or the number of vectors in the column. So if the rank is equal to that, so we get here the rank for this one, the rank is equal to 2, right? So you come back and you look at this matrix, and we say, hey man, something is fishy, right? Because n is equal to 3. So and that, I think I put that backwards, and I apologize. Over here, this should be the number of columns, and I'll fix that up right when we get through. So my phone was talking. So we said that the rank has to equal the number of columns. And let me just say it like that. And that's crazy because that's what I remember. This book, I think he makes the statement in the reverse, and so I was trying to be bookish, but I should have just followed what I know. So again, that is interesting, and so let's skip back to where we were. Oh, No, I think I'm right. I think I'm right. I'm losing my mind. I think I'm right. Boy, I can talk, can I? That the rank of T is equal to the number of rows. And I think we're good on that. So here is the rank. The rank is equal to 2, and then the number of rows that we have is 2. And so we get yes here for that. Now, I think I was getting B and C mixed up. Let's come back over here to B. So I was looking at C, but I was looking at C over here, but looking at B over there. That's what it was. Ah, so now let's look at B. Okay, so B here goes with this guy. Got you. So for B, the rank is equal to 2, but you have three rows. So the number of rows does not equal the rank. So that's why we get over here no. And what my statement that I put in here, I had to put that in there uh, to make everything make sense, is correct, and I feel vindicated. Yes. So now the last concept, and then we'll look at some problems, and hopefully I won't confuse the heck out of you, right? Well, I can do that. Isomorphisms of vector spaces, and I hope I don't. Definition of isomorphisms: a linear transformation T that is one to one and onto is called an isomorphism. Pretty cool. Iso from Greek meaning the same. Um, Moreover, if V and W are vector spaces such that there exists an isomorphism from V to W, then V and W are isomorphic to each other. Okay, they're not saying much of anything, right? Um, Isomorphic spaces and dimension. Two finite dimensional vector spaces V and W are isomorphic if and only if they have the same dimension. So that's probably obvious, I think, from the information. Now, considering this course as it maps into abstract and modern algebra, one-to-one functions are called injective or injection, an injective function. Onto functions are called surjective, and functions are called bijective when they satisfy one-to-one and onto. Thus, bijection is the same as isomorphisms. Now we can look at some problems, right? So here it says define the linear transformation T as T of x equal to A of x. We're given the matrix A, find the kernel of T, and then find the range of T. So what we do is we reduce this matrix. Here's what we do. We set it equal to 0 and we solve. So we solve the homogeneous. So when we're dealing with the kernel, remember the kernel maps into 0, right? So we solve that. So this is what I do over here. So this is really a line dividing there. So I do that on the calculator, and so what that ends up giving me is x of 1 is equal to 0 and x of 2 is equal to 0. So that's why you get 0 comma 0. What is the range? Well, here's the thing. When you reduce the matrix and you end up with the identity matrix, and you have a 2 by 2 system, and you have two leading ones, then the range is directly the R2 space. Okay. And there's one of these problems on here that I think Web Assignment got it wrong, and I'll cover that, and I'll show you. I'll show you their answer, and I'll show you my answer. Obviously, I guess if you want to get it right, you put their wrong answer in there. But I think just to know the right answer is from when I work it out, I think is best. And I will I'll try someday to reach out to WebAssign and see if they can get it corrected. Okay, so we do the same thing. We're going to set AX equal to 0. And solve. So what we end up with, basically, we're going to just try to reduce this guy as well. So we have 1, 0, negative 1, 1, 3, 3, 0, 0. So I'm going to reduce by, I'm going to add row 1 to row 2, row 2 to row 1, excuse me. So we get 1, 0, 6, 0, 0, 1, 3, and 0. Now you notice that it's lopsided. We have 3 columns, 2 rows. So you know you're going to have infinitely many solutions, right? Here we talked about it, I think back in chapter 1, to determine if it's going to be infinite many solution, subtract the number of columns from the number of rows, and that tells you what the floating parameter is going to be. So we have x sub 1 minus 6, x sub 3 is equal to 0. X sub 2 plus 3, x sub 3 is equal to 0. So we're going to let x sub 3 equal to t. So we end up with x sub 1 is equal to 6t, and x sub 2 is equal to negative 3t. Right? So here, this kernel, the values that map into 0 would be the set that we just found. We got x sub 1 is 6t, x sub 2 is negative 3t, and then x sub 3 is t. And we get them there. Okay. So here it says find the range of t, and it says that the range. Now watch this. We look at these guys and we say, you know, could it be this, or could it be that one, or could it be that? And you have to rule them all out, because these values are not even in the reduction of this, right? If you know the idea, if you were to reduce this, you would get something like 2t negative t, or something like that, if you're looking at you know, those two components. Now why are they only concerned about x and y? Here this is the range. The range values, where do they map to? Let me show you what's happening so you can see it. This a times some vector x is equal to some vector w that's in the range. Now remember, for matrix multiplication, this is a rows and columns, so this is a 2 by 3. So which means that I need to multiply by a 3 by 1. So I have a, which is 1, negative 1, and 3, 0, 1, and 3, times a 3 by 1 matrix. So I'm going to call this X, Y, and Z. So this is a 3 by 1. This is a 2 by 3. Look at the size of the result. The resulting size is a 2 by 1. So what's going in the range is a 2 tuple vector, right? So this range looks like this is x minus y plus 3z. That's just one value. And then this is y plus 3z. And I could have, this is in the range. If I had put numbers there, for x, y, and z, like 1, 2, and 3, we would have gotten two numbers, right? So this guy here is a 2 by 1. So in other words, you have to rule out this term, and this term, because the reduction of this is not that, right? And you have to rule out R, because this mapping, this transformation, is mapping into the range size here of a 2 by 1, which is equal to, oh boy, that's too fancy, which is equal to R2. Sorry for taking you all around the world. All around the world. Same song. Supposed to be a check. Alright. Okay, what about this one? So, okay, we did answer all the questions over there. So we look at this, and it says define this linear transformation as that. Find the kernel, find the nullity, the range, and the rank. So we take this matrix and we solve. I'm solving the null space, and you can see from my graphing calculator we end up with this, right? So here you can see that x of 1 is equal to 0, and x of 2 times 1 is equal to 0. So we get the kernel there, right? Now the rank is 2, right? Because you count the number of vectors that I have, the number of leading ones that I have on the main diagonal. There's 2. And n is equal to 2, right? So n is equal to 2, the number of rows. So the rank theorem says that the rank of t plus the nullity of t has to equal to n. Well, if I have 2 for the rank plus the nullity of t is equal to 2, then that has to imply that the nullity is equal to 0. Okay. And notice here that we have 2 leading ones, and we're already in the 2 space anyway. This system is mapping, is doing this mapping. This t is saying vectors from R2 into R2. So we're here. You can always rule these guys out when you have the identity matrix. To get the identity matrix means that we have the unique solution, and then for the null space we have the trivial solution, the solution of all zeros, which is what you get here for the kernel. Okay. For this particular problem, we are given a matrix A, which basically represents the transformation of T, so that T of x is equal to A times x. So to multiply the matrix A times a vector x then gives us the transformation or the function. The result of the function we call the range. So here, find the kernel of T, the nullity of T, the range of T, and then the rank of T. Now the kernel and the nullity are related. The nullity is just the number of vectors in the kernel. The kernel of T is the same as the solution space for AX equal to 0. So when we solve AX equal to 0, we are actually getting the kernel of T. So if we take the matrix here and just reduce row echelon form, and this is what I'm doing over here, notice that what we have is in this reduction so we set the system equal to 0. So this gives us x of 1 is 0, x of 2 is 0, and so from there we can stop and know that we only get one vector that has these zeros in it, and it's 0, 0. And so this would be the so-called kernel of T. The nullity is 0. So nothing here works out for us. And so it's not like we get some kind of vector or vectors that depend on some parameter. If that were the case, then we would have at least one vector within that so-called solution space. So not too much there. Now when we get to the idea of the range, you have to go back a while, a few slides up, where we talked about the range is in the column space. I don't know if, let me see if I can pull that out. So here we have this T, a transformation, goes from Rn to Rm, is linear based on the matrix multiplication of A times X. Then it says then the column space of A is equal to the range of T. Well, that gives it to us, and then the number of vectors that's in the range is the rank, right? This number of, or dimension. Okay. So with that said, if and since the range is in the column space, then you notice on your graphing calculator the reduction is based on row reduction, row reduced echelon form, or row echelon form. So it does not do column echelon form, which, I mean, the idea of that is happening, but not directly, somewhat indirectly. So since the range is in the column space, we must convert the matrix to its column representation to be able to reduce row echelon on our graphing calculator. To do that, we just simply take the transpose. So transpose A, and you take the transpose of the matrix A, and this is what we get. and then from the transpose, then we reduce for echelon form. Now, when you do that, then you have this reduction. Now, I'm going to go back and just write it back the way it should be, and that is we have 1 0 1/3 0 1 negative 1/3. Okay. So here we're trying to find the range of t. Now the range is set to be in the it's in the column space. Now notice here that in matrix multiplication, the range is the result, right? The domain is the preimage, and the range is set to be in the codomain. So I need to multiply this, the given matrix A is its reduction, times a vector from the domain. Now here, since this guy likes to use S and T, I don't. But S and T are from the domain. Now notice that the matrix A is a 3 by 2, and this vector from the domain is a 2 by 1. Now that's going to give us a 3 by 1 matrix. This 3 by 1 matrix will be in the range. So we multiply row times column, so this gives us S. Then here we multiply, we get T, and then here we have S over 3 minus T over 3. Now, in looking at that, you can just do an equivalence by just multiplying 3 by 3. And so you can write that as 3s, 3t, and then this would just be s minus t. And so that gives us this choice here. Now to get the rank, you can quickly just say that based on the leading ones, I have 2 leading ones, so the rank is 2. Or if you want to just really look at it to see exactly what those vectors are in the range, and to actually count, because the rank means the number of vectors that I have in the range. So you take this 3s, 3t, and then here this is s minus t, and I probably should have left it in the original, but this is fine. So here this is, I think I prefer maybe the original, but this is okay. So here this is 3 just times the s, so this is 3 0 and 1 times s plus, there's no t there, there's 3 times t and minus 1. So when you count, oh, that's times t. So the so-called basis for the range would be these 2 vectors there. There's 2 of them, and so that implies that the rank is 2. So that's it. Now one thing to note, now because of this matrix multiplication, you have this matrix A times some vector x, that gives us some vector w, where you have this x that comes out of the domain, and you have this vector w that's in the range. Now, what gets you from the domain to the range? It's the multiplication of the matrix A. It's the multiplication of A. So it's the multiplication of A that defines, that is the transformation. So a lot of talk to the somewhat say almost nothing, right? I think it was this problem that I had issues with. The last one, and then I leave you alone. Does the matrix define a linear transformation T that is one to one and onto? In other words, I put this caption here just to kind of explain. In other words, is T an isomorphism? To show that T is one to one, verify that the kernel is indeed the zero, maps into the origin. That is, the null space AX equal to 0 only yields the 0 solution. To show onto, verify that the rank of T is equal to the dimension of the range. That is, the rank of A is equal to the number of rows. Boy. Okay. So we have this matrix, and I'm going to reduce it just to see if I see what's happening. We're going to interchange rows 1 and 2. It's going to be 1 0 0 0 0 1 0 1 0, and then now I'm going to interchange rows 2 and 3. Okay. I mean, I think right there you get it, and you can stop. This is already just reduced into the identity matrix. I mean, that's the perfect form, which says it's a 3 by 3, which says the rank is equal to 3, the nullity is 0. Right? And so if you have that, then you have one to one and onto all together. So, but just working it out, look at AX equal to 0, and we just set this system here equal to 0. So that implies that x sub 1 is equal to 0, x sub 2 is 0, x sub 3 is 0. So we get this kernel of T is equal to 0, 0, 0. So here that defines, shows that it's 1 to 1. And then for onto, now the rank of T, notice that I have 3 leading ones, so the rank is equal to 3, and n, the number of rows that we have, is 3. So we said that if those numbers are the same, then that the transformation is indeed onto. So T is indeed an isomorphism. Well, let's stop right there. Thank you.